Hi everyone. In this video, we're going to talk about shrinkage and penalization methods that we're picking up after um, the stepwise, the stepwise selection methods. Okay, and so these are generally preferred a little bit more. So if you, when you watched my last video, I mentioned a couple times that people don't like the stepwise selection methods for various reasons. Some of them are worse than others. So some methods use a p-value approach to add and subtract. People really hate that. Um, but in general, these stepwise selection methods are not looked upon favorably by a lot of people um, for various reasons that we won't really get into. And so here I'm going to introduce other methods that do something similar that people like a little more, uh, but they also have some issues with. And um, there are not going to be any methods that people don't have issues with, we're going to say. So it's not necessarily that these methods are bad. I guess I would push you away from using those stepwise methods a lot in practice uh, for a couple of different reasons. But anything that I show you, I'll mention if I know them and if I think they're relevant, what people like and dislike about them. Um, and every method is going to have that because we're not at the cutting edge of what's happening today. We're not anywhere near that with these, but these are in essence at one time were cutting edge methods and are implemented a lot in practice, and so it's important to know them. So anyway, I'll stop my soliloquy on goodness and badness of these methods, and we'll get to them. So instead of fitting a bunch of subsets, we can constrain or regularize the coefficient estimate. So instead of fitting a bunch of models and see which ones are good and bad, based on regular fitting criterion, and when I talk about that, I mean using just trying to find the solution, or rather the solution to the problem is the coefficients that minimize the residual sum of squares. That's regular linear regression. The stepwise methods just fit linear regression a bunch of times and see which one looks the best. Okay. Now we're going to change our fitting criterion. So it's not just going to be residual sum of squares anymore that we're looking to minimize. And that's what we're regularizing or constraining. So the idea is that the coefficient of the predictors that are the least correlated to the response are going to be shrunk towards zero and give us essentially a best subset of the predictors. And you'll see what that means a little bit more clearly when I start to show you pictures and we go through these methods. Okay, there are three of them: ridge, lasso, and elastic net. And you'll see each of them. Elastic net is a combination of ridge and lasso, just like a little bit before, where you combined forward and backwards to get that stepwise or both selection. But anyway, let's get to them first. So we'll look at ridge regression in a little bit more detail, and then the other two are going to follow similarly, and so I won't do quite as much detail on those. So usually you choose the coefficients to minimize that top thing, so we're just minimizing residual sum of squares. Now what we're doing is we're adding essentially a bias term. So we haven't talked a lot about bias before. The bias is, we won't quite get there yet. We will talk a lot about bias, but bias is essentially, it's something that's not at the theoretical truth. It's away from the theoretical truth. And so in terms of linear regression, you just want to minimize the residual sum of squares. But now I'm adding this penalization term. So maybe not a bias term, maybe that was incorrect of me to say, but at least we're going to call it a penalization term. And so I'm going to penalize something. And so if you look here, it's the same. So a ridge regression coefficients. If you look, it starts with the residual sum of squares. So I want to do that. And then I add on a term. And so I add on lambda times the sum of beta sub j squared, where beta sub j are our predictors. And so what I'm penalizing here, again, a big residual sum of squares is bad. So I'm adding things on which are going to make them, so I'm adding things on, bigger things are worse. And so what are we penalizing here? I'm penalizing large beta values. And so what happens is that as I add more and more penalty to this model, meaning, so if lambda is really, really small, it's a really, really small number, okay, 0.00001, no matter how big the betas are, I square the betas, yeah, no matter how big the betas are, it's not going to inform the model that much. It's not going to change the model that much. But as lambda gets bigger, then that penalty is going to take over. And I don't really care about the necessarily right answer. I only care about small coefficients, because that's what's really going to control my r squared. And so that's the idea of this ridge regression, is that lambda is what we're going to call a tuning parameter that controls the impact of the regression coefficients. It might be two of them, so I say two terms here. That's for simple linear regression, but it could be many terms if we do multiple. Excuse me. Okay, so when lambda is 0, that's no impact from this penalty or regularization term. So it's least squares, the usual thing that we're used to. Okay, and when lambda is infinity, or as it goes towards infinity, limit sort of thing, all the coefficients are going to get really, really close to 0. Now they can never, because of the squared, because of the construction of this, they're never actually going to get to 0, which is something that's different when we'll see lasso. Okay, so ridge regression. For standard, so some special considerations. For standard least squares regression, the usual stuff, the coefficient estimates are what are called scale equivariant. If I multiply a predictor by a constant c, that simply leads to the scaling of the least squares estimate by 1 over c. That means that we talked about centering and scaling before as things that we could do to change the fit or change the numbers. And what this is saying is that for regular linear regression, that doesn't do anything. It doesn't fundamentally change the model. It just changes by a constant c. Okay? Now, so we didn't really need centering and scaling for standard least squares, regular regression. But ridge regression estimates change substantially when predictors are multiplied by a constant because of this badness of being large. And so centering and scaling, not so important for regular regression. It's going to be very important for ridge regression. Okay. Now, the question is, why would you use ridge regression? And so why would I do this? Why would I add this different term onto residual sum of squares? Well, it can provide some improved behavior over least squares, okay? And the reasons are rooted in this thing called the bias variance trade-off. And I would talk more about this in class, and I want to do this less so in a video because my videos are already long enough. But there's this idea that unbiasedness is a good property. So to be unbiased is, in theory, your estimates, if you use certain estimates, such as regular least squares, you're going to get in theory, you're going to get the truth. Or rather, those estimates that you create are centered around the truth. Okay, it's a more nuanced argument maybe than that. But sometimes when you have unbiasedness, which is a good property, you might also have a high variance. So you can have an estimate which is unbiased, which means in theory or eventually as the sample size gets larger and larger and larger, your value of your estimate is going to get closer and closer and closer to the truth, and eventually it'll get to the truth because it's unbiased. But that estimate in the small sample case, when there's not a lot of data, it might be really variable, meaning however you calculate it, there's a lot of variability in the numbers when sample sizes are small. As it gets bigger, it gets closer and closer and eventually gets to the truth. But in the small sample case, high variance. And so the question is, do you really trust that estimate? Or so I have least squares is no bias, high variance, which means larger mean squared error, generally, for our purposes. Okay, whereas ridge regression induces or puts in this extra term that is going to bias the estimate. It's going to bias the estimate towards it being small because it penalizes that way. But in the small sample case, so it might not get to the truth, we'll say, in the large sample case. But in the small sample case, it might be actually closer. It might have less variance, less variability, and hence might be closer to the truth. And so if you induce some bias, you might reduce the variance. Okay, so anyway, I probably made the video too long anyway there. So that's bias variance trade-off. Now, situations where least squares has high variance. So you might say, well, it doesn't seem like that method would have this high variance, and in the estimates, and usually it doesn't. It's not always terrible, but there are a few cases where they are terrible. And so what are those cases? Well, when there are multicollinearity between predictors, and remember that's when two predictors contain essentially the same information. We talked about the case where it contains the exact same information, and that's a big problem. But when it contains essentially the same information, the model will fit, like it will run, and you will get results. But it is what people would call unstable. And what they mean by unstable is you get high variance, high variability in the estimate until you get a large sample size. Okay. Second is when P is close to N. P is the number of predictors you have. N is the sample size. So when you have a lot of predictors, not a lot of data, then you have high variance. And also, even worse than close to N is more than N, which can be a big problem when you have more predictors than data. And that is usually not the case, and not going to be the case for many of our situations, but can be the case for certain types of data. Okay, ridge regression. Sorry. Here we're going to use a model. We're going to try to fit ridge regression. Excuse me. So we're going to fit ridge regression with something called, or rather functions called functions from the GLMNet package, a very popular package. So GLMNet package needs the data in a certain way. And that way is a matrix as a matrix of predictors, and a sorry, a vector of responses. So a matrix of predictors, a vector of responses. And this gets to something that I mentioned before, I believe on Thursday, when talking about tidy models and why we would use different models. And what tidy models does is it tries to fit these models in a common syntax. And so that's a great example here. With the LM function, we just supplied the data and told the relationship. Supplied the data and said, here's the relationship we want, let's fit it. Okay, well now the GLMNet package works totally different. In the GLMNet package, it needs a matrix and vector, which can be very annoying and something that tidy models looks to fix. Yeah? Okay, so anyway, matrix, vector. Next, I need to define what the lambdas are. Or rather, I need to define a lambda at least, but maybe I want a bunch of lambdas. And so here I fit a bunch of lambdas because, well, I don't know what the best is, and we're going to find out ways in which you can fit the best or find the best one. Using something called cross-validation, but we'll get there. We're not there yet. So I have a bunch of lambdas, and I fit them. Now, big lambdas are going to be terrible, and so I want to fit a bunch of these lambdas from very small to very big, but not on a linear scale, because really large lambdas are going to be really bad. I want to fit them I want more of them on really small numbers than on the big numbers, because the really small numbers, that's where usually the best lambda is going to be. So I devised a clever way to get more small numbers than big numbers, which is look at these numbers on a log scale. Okay, so I do that. I fit ridge regression. Okay, and now I'm going to give you this code to make this graph, this special kind of graph, which is showing you how the coefficients behave for all those various types of lambdas. So x-axis is lambda, y-axis are the size of the coefficients. And so this picture looks like almost immediately they shrink down to 0, which should make sense because the higher lambda is, the more penalty you're adding in, and so eventually you don't care about the fit anymore. You just care about the predictors being small. So let's zoom in. We're going to zoom in here from lambda is 0 to 150. Okay, and so you see some interesting behavior here for these different lambdas. Now you see they're shrinking to 0 in this x squared sort of fashion, which should make sense, because that was the lambda that we picked. Or rather, ridge regression is this squared loss sort of thing. Okay, but you see interesting behavior, especially this blue one, which looks to be, although the colors over here are a little crazy. So x2 is this yellow one, the top one. Okay, x3 is the green one. x7 is down here, the purple one. And then this last one here looks to be x6 maybe, which doesn't necessarily make sense. x4 was the other one that might have been in there, but nonetheless, you have this interesting behavior in which blue turns from negative at the beginning to positive after some loss was put in there, and that seems quite odd. If you think about how each coefficient behaves, that the behavior would flip not only how big it is, but also the sign, that it's negative at first and then turns to positive, which is really interesting and shows you in how these work in tandem. Okay, Also, the green one, x3, has a little bit of interesting behavior, that it goes up and down. That might be due to the sinusoidal nature that I gave x3. But now the question becomes, where do I cut it off? At what lambda does it seem like it's right? Because eventually, even these down here, probably at like 25 and beyond, they aren't right anymore. Like my coefficients aren't even sensical, we'll say, anymore. They're just small numbers because we have a lot of penalty associated with them. So really, the cut is going to be way down here at 0. Almost no penalty compared to all of these. But I wanted to give you an idea of the shape. Now, the question is, which one do I choose? And we're not really going to talk about cross-validation in theory, but I am going to show you cross-validation. It is a way that looks at a bunch of different subsets of the model to choose the best lambda. And so I do that here by giving them all of the lambdas. There are these folds, so on and so forth. I'll talk about this more in person before I ask you to do any sort of cross-validation. But anyway, it is some method that gives us a best lambda. And then I pick out the coefficients that was, or I can, using that function. It'll tell me all of the coefficients. And so essentially that's the model that I want. So now, let's look at the other ones. So the second one is lasso, the lasso. So I show you here regular linear regression, ridge, and then lasso. Notice that the only difference is instead of squaring, I now take the absolute value. Instead of squaring, I take the absolute value. That changes some things. Okay? Very similar formulations between the two, but there are differences in the penalties. And so the few differences are, both of them shrink estimates towards 0. That's true. But because of the absolute value argument and the difference between absolute value and squared is that the lasso can actually shrink a coefficient to 0. Ridge can only get arbitrarily close. But the lasso can actually take out coefficients. And so in that sense, the lasso can actually perform variable selection. Okay? So you actually use the same function, this glmnet function, to do lasso. And before, if you look back, you'll notice alpha is 0 for ridge, alpha is 1 for lasso. And you'll see, based on the elastic net actually, you'll see why I'm using alpha alpha as 0 or 1. Okay, and so I'm going to do the same thing. Here's lasso. And so here you notice a very different shape. Okay. Very different shape, but now you notice that immediately things are actually going to 0, not getting arbitrarily close. Yeah? So that's the lasso. Last one, elastic net. If you look down at the bottom, it's a combination. I guess you would say, actually, the correct term is a complex combination, convex combination of lasso and ridge. So you notice this alpha parameter, which is how much lasso and ridge do you want in between. So if you said alpha is equal to 1, that's all lasso. Alpha is equal to 0, that's all ridge. So that's why alpha was 0 and 1 before. And then anything in between is this elastic net. And so what elastic net looks like is this. So it has that x squared shape to it. It has that sort of nonlinear shape, but also can shrink stuff to 0. So it's a nice in between. But also with the elastic net now, you have not only the choice of lambda, but also the choice of alpha. So what do I make alpha be? Anything in between 0 and 1. And then what do you make lambda as well? Okay, and so here is some code to help you tune alpha and lambda. Okay, again, we'll go over this more later on. But that is based on this code, which is, again, some of this cross-validation stuff. This is using a package called Caret, which was a precursor to tidy models. The same person who made Caret also made tidy models. Okay, it gives you best alpha and lambda values, and that's where you would actually cut it. So notice not very far at all into these lambda values, into the penalties, but it gives you something. And so that's the end of model evaluation and regularization.